Welcome to VINDAL'S concept, and today I want us to look at a very important topic, the one that students find it very difficult to handle, and I've come today to reduce that problem. And today, what we are going to look at is linear velocity and angular velocity, the relationship between these two concepts. Linear velocity is given as v. This one is linear velocity, or should I say speed, linear velocity or speed. Then when you see this symbol is given as angular velocity or angular speed. We are going to look at the relationship between them, which is given as v, this multiplied by this, or it is given as v equal to a omega. So we are going to look at the relationship between these two. But then, as the lesson is going on, I want you to try your best to be listening to the explanation while you also watch the video clip that is pasted on the screen. This will paint the better picture of what I am explaining to you. If you are ready for this class, get your pen and paper and let's get started. All right. All right. In this part, I want to start by considering a body in a circular motion. This body in a circular motion has a center, and then the body, should I say that the body started from a point and moves to another point, say point B. Now, as this body is moving, I'm going to make it look like a body of mass. This kind of motion is called circular motion. It is a circular motion in the sense that this particle at this point A moves around this circle with a constant speed. I said with a constant speed. And before, as it started moving on this axis, it opened an angular displacement called theta. But this angular displacement, theta, is going to be expressed in radian and not in degree for the sake of our concept. And I want you to know that anytime a circular motion is on, whenever a body is undergoing a circular motion, it is at the same time undergoing a simple harmonic motion. The video you're watching is showing that there is a relationship between a circular motion and the simple harmonic motion. The only difference between circular motion and simple harmonic motion is just the fact that the acceleration of the circular motion is not directly proportional to the displacement. Unlike in simple harmonic motion, acceleration is directly proportional to the displacement, and the acceleration of the moving body is always directed towards the center of the circle. So, but this one, the only thing here is that the speed is constant and that the acceleration is not directly proportional to the displacement as it was given in simple harmonic motion. However, I'm going to do a proof to show that this is true. Now, if I drop down, if I have a vector drop down, if I form this triangle, this is center O, I can call this P, X, I can call this point, let's say point M. Now, for this body, this particular position, this P now, as it is moving around the circle, it is also doing like this, and this is the nature of the simple harmonic motion of this point on this axis. What I mean is that this position M is moving like this, which is simple harmonic motion, up, to and fro, to and fro, to and fro. That is simple harmonic motion, and at the same time moving in a circular path. If I do this, remember from this center to the circumference to the highest point is represented as R, or the amplitude. So if I use this O, B, and M, I realize that the angle is cos theta is equal to what? Adjacent over hypotenuse. This is adjacent over hypotenuse, which is R. So I have that X is equal to R cos theta. So that means that this distance from O to this M is given as the radius or the amplitude of this body in a circular motion multiplied by the cos of the angular displacement of the theta. And I'm going to call this one equation 1. I'm going to make one more assumption, not assumption, a fact. There is something we call angular displacement, and that is given as, there is something we call omega. This symbol is given as angular velocity, and angular velocity is given as angular displacement all over time. Therefore, theta is given as this multiplied by t, omega t. I am going to substitute this in this equation 1. So I'm going to have x is r cos omega t. Removing theta, I'm replacing it with omega t. So this is another function also for a body in a circular motion and also undergoing simple harmonic motion. So at this point, I am going to take a derivative of x with respect to t, because I want to achieve velocity. And remember that this x is representing a displacement. Now, this x is going to be dx with respect to dt is going to be equal to v. Have that at the back of your mind. Let this be at the back of your mind, because rate of change of displacement with time is what velocity explains. However, I want to do the derivative of this. I'm going to have x is equal to r cos omega t. Now, I'm going to say let u equal to omega t. So I'm going to say du with the t is going to be equal to omega, because t, deriving t is that there is a power of 1 here. 1 times w is w, and 1 minus 1 is 0. So anything raised to the power 0 is 1. So that is why I left off with this. Now, after this, I'm going back to this to say that x is equal to the radius or the amplitude cos. Remember that this particular concept or function is no longer there, is given as u. All right? I am going to apply chain rule. I will call it function of a function. This is use of derivative for this proof. So I'm going to have the x du. The x of this function with respect to u function is going to be minus r minus sine u. Remember? And then I am not touching this one. I'm just touching it, just a multiple of the function. I'm not touching it. So this is what I have at this point. Now, at this point, what I'm going to do is, the final step is going to be, I'm going to say this multiplied by this. So the chain rule there is this. So the chain rule is going to be, remember my intention was to derive the displacement with respect to time. And that's going to be dx all over dt. And that is going to be equal to, the first I did was du dt. So I'm going to have du dt times. The second one is dx du. Dx with respect to u. So if you see that, if I manage to if I cancel this du and this du, I have dx dt. And that is to prove that my chain rule is correct. This is called chain rule. All right? So what is the next thing? So at this point, I'm going to substitute the values that I got from my expressions. So the u dt is omega. So the x dt is equals to the u dt is omega multiplied by the x du. The x du is this minus r sine u, right? So, and the whole expression becomes minus omega r sine. Instead of writing u, remember that they said that u is omega t, because I want it to be left with the function of time. So I say omega t. Therefore, the x, the v, the x, the t is same thing as v. This is expression for velocity of a simple pendulum, of a simple harmonic motion, which is having the same relationship with a circular motion. And this is it. Now, to obtain acceleration, I am going to derive the v dt is given as acceleration. So, and I have v is equal to minus omega r sine omega t. So the same thing I said, I'm going to say let omega t be u. So the t is going to be omega, right? So this becomes v is going to be minus omega r sine u. So what I'm going to say now is this. The v du is equal to, the v du is going to be minus omega r. If you differentiate sine u, you are going to have cos u. Differentiation of sine u with respect to x, you are going to have cos x. So I'm going to now go further. So the v dt is going to be, the v dt is going to be du dt times dv du. So that if I cancel the u and cancel the u, I'm having this, which is the same. That's correct. So I have the v dt is going to be du dt is omega times the v du is minus omega this cos u. So now remember the v dt is same thing as acceleration. So I'm going to say acceleration is equal to omega multiplied omega is minus omega square, and then why am I using a? I'm supposed to be using r. R is what I'm using here, please. I'm not using a, it's r that I'm using. So they are interchangeable. Look at them. So it's all right. So I'm having omega multiplied omega square r cos u. But instead of writing u, remember that I said that u is omega t. So I'm going to put this omega t. So we have that acceleration is equal to minus omega square r cos omega t. Look at this. What is that? That was given from this expression. If you look at this expression, I said that x is equal to r cos x. Cos theta. and which was given that S is equal to R cos omega t. So if I remove this for this, I'm going to say that A is equal to minus omega square multiplied by X. This is an expression for angular velocity. This is an expression for acceleration and angular acceleration. Why this can be given as a function for the angular linear velocity and angular velocity, which is also this function. This and this are of the same function. However, you must try to please hit that subscribe button. Subscribe to this channel. I am going to promise you more of this kind of content will be boosting your channel. Just stay put. Be loyal to this channel. I am going to give you the best you have ever imagined. If there is any topic you want me to treat on physics, mathematics, on further maths, do what just to hit me. I'll get you covered. Thank you and remain blessed from VINDAL'S concept.